Hello for everyone joining us on Zoom. My name is Josh Gilliland. I'm the chair of our marketing subcommittee. We are getting started and connecting our live stream to Facebook so we can share this with everyone who is online as well. And we had a lot of people sign up for this one, so we are super excited. And I have fond memories of learning tides and currents and look forward to our presentation tonight. All right, we are connecting slowly to Facebook Live. Wait for it.
You're muted, JD. Okay.
All right, and we are now connecting. Hope everyone's doing well. There's been a lot of great activities that we're starting to see take place across the country. And for everyone who's able to do in-person meetings, keep posting to social media. We love seeing everyone's adventures. And we are now live on Facebook as well. So for everyone who's joined us on Zoom and everyone who's now joining us on Facebook, my name is Josh Gilliland. I'm the chair of our marketing subcommittee. With me is Bruce Johnson, who is our Coast Guard Auxiliary Liaison, and Lieutenant John DeCasta, who is a helicopter pilot and has been one of the key forces in organizing all of our webinars this year. And it's great to have JD with us tonight because he is a fun presenter. And let's get into tides and currents. So Bruce, the floor is yours.
Thanks very much, Josh. Good evening, everyone, and welcome to our monthly Coast Guard Tech Talks workshop. These workshops are jointly sponsored by the U.S. Coast Guard, the Coast Guard Auxiliary, and the Boy Scouts of America's Sea Scout program. My name is Bruce Johnson, and I serve as Chief of the Coast Guard Auxiliary's youth programs. Our co-host is Josh Gilliland, Chair of the National Sea Scout Communications and Marketing Team. Josh will be coordinating your questions in the third part of the program. Coast Guard Tech Talks are held on the fourth Tuesday of the month at 2100 Eastern, 2000 Central, 1900 Mountain, and 1800 Pacific time. Each program focuses on a single science, technology, engineering, mathematics, or STEM topic. These topics are chosen to support the Sea Scout Advancement Program, and next month's Tech Talks workshop will be on engines, which is one of the Level 3 advancement electives. Tonight's topic is Sea Scout Able Requirement 10G, Tides and Currents. Our presenter is Coast Guard Lieutenant John DeCasta. Lieutenant DeCasta is a graduate of the Auxiliary University program at Auburn University in Alabama. He enlisted in the Coast Guard in 2012 and served on the Coast Guard cutter Gallatin. He was accepted to Coast Guard Officer Candidate School and upon graduation was stationed as a deck watch officer on the Coast Guard cutter Diligence. From there, Lieutenant DeCasta served as the response department head for Marine Safety Unit Huntington. From there, he went to Navy Flight School, graduating in 2018, and is currently stationed at Air Station Atlantic City, New Jersey, where he flies the MH-65D Dolphin helicopter. So one last thing, we've muted your microphones to make it easier for everyone to hear. If you have questions, type them in the Q&A box, or you can use chat. Josh will be monitoring the chat and will be sure to leave time to answer your questions at the end. So let's welcome JD DeCastro.
Welcome. I'm excited for this one. I'm coming back to going back to my cutter days on ship, talking about tides and currents. This is going to be a fun one. And first, I do have to apologize for being a little overdressed. I've recently been quarantined at home due to some stuff at work. And this is the only uniform that I actually have at home. So you get to see me in my full best. But anyway, without any further ado, let's jump into it. So I'm going to be doing a mixture of both PowerPoint and just talking with my hands because I like PowerPoints, but they can get a little cumbersome. So we are going to come to the front of here. Let me share my screen. Host disabled attendee sharing screen. Josh, is there any way in which we can?
Try again.
Beautiful. All right, here we go. Share this. All right, come here. Let us kick this off. Excellent. All right, tides and currents. So we're going to be talking about tides, tidal progression, currents, and then going into some NOAA sites to where we're actually going to get down into the nitty gritty and actually see what these talk about or see what these are. So, okay, so let's start about tides. Before we get into it, we got to talk or speak about what actually influences all of this. And this is all coming down to the sun and the moon in relationship to the earth. So the sun and the moon both produce gravity, or they create gravity along with the earth. And these gravitational pulls or forces of the moon and the sun are what actually pull the water and have it bulge towards the equator and away from the poles. So we have our solar gravitational force and the lunar gravitational force. Now you'll notice that the solar one in here is actually smaller than the lunar or the moon. That's because the moon is closer to the earth. Therefore, it exerts a larger gravitational pull and is more influential on the tides than the sun. However, the sun still influences it. And the way this works is, so we have two equations up here. They're somewhat good. Now, when you actually dig into it, there's a lot more that goes into play, but simplifying it down, we have the gravitational force here, which is going to be indicated by these goldish arrows, and they're pulling the water towards whatever body it is identified by a satellite, whether it be the sun or the moon. And that's going to be dependent upon the mass of both bodies, how far away they are, and a gravitational constant. So the closer a body is, the stronger the gravitational force, and the larger a mass, the closer the gravitational force. Hence why the sun, even though it's a lot further away than the moon, still affects the tides because it is significantly more massive than the actual moon itself. Now, the other one, you'll be thinking to yourself, okay, well, if in this picture, the sun and the moon are all on one side, why am I getting a bulge on both sides? Still affects the tides because it would make sense that you would only get it on one. Now, this is where Newton's laws of motions come into play. And in this one, it's called the inertial force. So for every action, there's an opposite and equal reaction. So as the tide's being pulled this way on the other side of the earth to help compensate for the conservation of energy, you have to have some type of bulge this way. And that's inertial force. It's also indicative of the rotation of the earth, indicated by V. So the V is going to be, the V squared over R is essentially a fancy way to take angular motion and convert it into something we better understand as linear motion. So since the water is on the surface of the earth and the earth is rotating, that water has some type of velocity to it. We can't perceive it because we're rotating at the same speed. However, in the grand scheme of things, it does have speed. And that speed forces it, just as if you were to take a pendulum or a ball on a string and fling it around, same principles happening here, causing the bulge out that way. And you get these two opposing forces on both sides of the earth, which result in your net tidal force of pulling the water that way or pulling the water this way, where you get your tides and tides and currents, I should say, because both are dependent upon the moon. So now we're going to get into actual tides. And this is where I'm going to stop sharing my screen because I don't like PowerPoints. So tides and currents. So what is a tide? We're going to talk about tides first because they are more important to everything. And I can conceptualize it better, and that's why we're going to talk about it first. So tide is the horizontal movement of water. You have your low tide and your high tide. It's either muddy or the water's all the way up. That's all the tide is. And we have multiple different kinds of tides. We have the three predominant tides are diurnal, semi-diurnal, and mixed. And I'm going to show you examples of these here in a minute. Diurnal essentially means you have one high and one low a day. This is predominantly on the Gulf Coast. Semi-diurnal, you have two highs, two lows per day, and that's going to be on the East Coast. And then for you West Coast people, you typically have mixed, where you have a variation. It's similar to semi-diurnal, but the highs are not as high and the lows are not always as low. So when you have semi-diurnal, your highs are pretty much always constant up here, or your lows are pretty much always constant down here. With the mixed tides, you might have a high here, then a high there, a low there, and then a low down here. It's mixed. And then you also have spring tides and you have neap tides. So spring tides, and these are in relationship to the moon. So spring tides typically coincide with your full moon and your new moon. So when you have that, the sun and the moon are on either opposite or the same side. So those gravitational forces are in addition to each other and therefore stronger total gravitationally speaking. And because of that, your high tides are higher and your low tides are lower. The opposite is going to be a neap tide. That's about 7 days after, roughly speaking, because the lunar cycle is around 15 days. Don't quote me on it, but that's the number that comes into mind. So 7 days after your spring tides when you're going to have a neap tide. And that's where the highs are lower and the lows are higher. So instead of a high way up here, the high is going to be here. And instead of the low way down here off the screen is going to be closer. So the difference is going to be different. And how that's going to kind of visually speaking here. If we were, I'm going to try and do this. All right, so so this configuration we have right here with the sun and the moon is going to be our spring tides. If I can drag this moon all the way over here to halfway through its lunar cycle, this is where you're going to be getting your neap tides. Because now instead of this gravitational force both being here, we have one out here and then one up here. So now let's show some pictorials of the diurnal. So this is a diurnal tide. You can see we have one high and one low in our 24-hour period. Our semi-diurnal, we have two lows and two highs in our 24-hour period. And then our mixed, similar to the diurnal where we have the two lows and the two highs, but if you'll notice, the highs are relatively the same, whereas here they are not. And what else does this get us? If you have a diurnal tide, you can also estimate when the tides are going to shift. So if you're doing a trip planning and you know, okay, low tide is going to be at this time, I have diurnal tide. So low tide's at 8 o'clock, I got diurnal tides. I can only get underway when it's high tide. So if it's 8 a.m., well, I can't get underway until 8 p.m. Or you know when you're coming into port, okay, I left at 8 a.m., it was a low tide. This was the clearance of the draft I have. Okay, 12 hours later, boom, it's high tide now. I know I had the draft to get out at low tide. I'm definitely going to have it come in on high tide, or opposite. If you're casting off at high tide, and it's like, ooh, barely squeaked across the bar on that one. Oh crap, I need to get in before 12 hours from now. Or if it's a semi-diurnal, ooh, I need to be in within 6 hours. Because now with it being two lows and two highs, instead of that 12-hour cycle, you're getting a 6-hour cycle between your lows and your highs. So it's a quick way without looking at the specific tide tables of estimating, okay, this is the area I live in. This is kind of what the tides do. So I can roughly say, all right, based upon this and that, here's the time that's elapsed. Or another example of applying this knowledge is I was working a search and rescue case where there was a boat that was beached pretty far up on the beach. So I knew, okay, there's probably a good 10, 15 feet between where the boat is and where the current water is. And it's X amount of time. You're looking at the environmentals of the buoy tails and you're like, okay, so the tide has been ebbing for at least X amount of hours. It's been within 6 hours since that boat was up on the beach. Okay, let me do a quick set and drift of, all right, 6 hours, they could be from here up to there. All right, let me figure this out. Meanwhile, the shoreside people are doing the more detailed math and getting me a more specific pattern, but it lets me, okay, nope, this is the rough area I should look in until I get the better one. And then same thing with the mixed. You have that period, but the height's going to be different. All right, so now we're going to talk about something called tidal progression. Tidal progression, I don't have any good slides on it because it's important, but it's really all you need to know is the tide rises and the tide falls. But there are two ways in it can do that. You can have progressive and you can have stationary. So progressive is like a bore wave. It is at point A and point B. There is a clear distinction between, all right, the tide is 2 feet higher here and it's 0 here. And you have an actual wave of water moving down through the body of water. Whereas a stationary wave is the water's here and the water's here, and they just kind of rise up slowly together. And that's your tidal progression. The important thing here is you'll note that we'll take the Delaware Bay, for example. At the mouth of the Delaware Bay, up to Philadelphia, which is, I don't know the exact distance, but it's a good trek, many, many miles. There's going to be a big time difference between high tide here and high tide there because that water has to move up. Now, depending upon what water it is and how close it is where you're going to get into your stationary versus your progressive. I wouldn't focus too much on, oh, is my area this or is my area that? It's more of a difference of, okay, I know that at point A and point B, roughly what is the time delay between the two? Because typically speaking, there will be some type of time delay, especially if you're transiting the entirety of the Chesapeake River or Chesapeake Bay, Delaware Bay. Unfortunately, I'm not familiar with my West Coast bays, but I'm sure there are plenty of bays out there who have similar, very large areas, big time gap between the two. That's the big thing with tidal progression. And we're going to kind of touch on tidal progression when we're talking about currents because they're not the same. And what do I mean by that? So tidal progression, you would think, okay, if the high tide is at 12 o'clock here and 1 o'clock there, I should be able to correlate a current speed to figure out, okay, how much water do I have to push through from here all the way up to there to equal the volume of water. All right, I got 1,000 gallons here. I need to push through at 20 gallons a minute in order to get to 100 gallons here too. You can't really do that. You just need to know, all right, high tide here, insert X amount of time, high tide there, and that's different between currents. Similar, but different. And with that is a great segue into currents. So we're going to talk about, just like tides, currents have multiple different kinds. And now what exactly is a current? So a tide is a horizontal movement of water. A current is a vertical movement of water. Think about it. This is where we get into interplay with tidal progression. I have, as the tide's moving in, the entire weight of the ocean is rising and trying to squeeze up into a bay, estuary, inlet, whatever it is. Well, that relatively infinite volume of water then has to push into that bay. So think of it this way. If I were to take a 5-gallon bucket over here and connect them with a line or a hose and another 5-gallon bucket here, I instantaneously fill up this 5-gallon bucket. Pardon my dog. That water is going to have to flow from this bucket to that bucket, and as it's going through that hose, it's going to have a speed or it's going to have a current progression. That's what's happening with current. That water is moving from point A to point B. Just like a tidal progression, but a tidal progression is not a current. I hope I'm kind of making that clear. If not, please ask a question or ask it in a question and I'll try and clear it up. So when you're talking about current, what exactly are you typically speaking or wanting to know? And that's speed. What velocity, meters per second, the engineer in me is coming out. The knots, how quickly is that current moving at? What knot is it? So if I'm in a boat, okay, I got a 10 knot ebbing current, I'm going outbound. Did I say 10? We'll make it more realistic. I have a 2 knot ebbing current and I'm transiting outbound, sweet, now I can tack 2 knots onto my speed. Or if I have that 2 knot flooding current and I'm going out, all right, now I have to subtract that. That it plays with my time, speed, distance, and it also affects how the ship's going to handle. So, and we do have multiple kinds of currents. We have a flood current, which is where, think of it as the bay or the estuary is flooding. The tide is coming in, it's going from low to high. So a flood current is that water pushing up into the inland body of water. You have an ebbing current, which is corresponding to an ebbing tide. So that tide is going from the estuary or the body of water out to the ocean. And the ebbing current is the speed of that movement of water. You have a slack current where nothing's moving. And then you do have a few other currents. The only one I'm going to talk about here is an eddy current. You also have a longshore current, a rotary current. Those aren't as important or as hit upon, but there are other different kinds of currents. And so what affects currents? The tidal progression does somewhat affect the currents. The quicker that progression, the faster that water has to move. Once again, they're not the same, but they are somewhat related. Moon. The moon, just like the moon affects the tides, the moon affects the currents. And it's in the same way as it affects one, it affects the other. So you're going to have your spring current, your neap current, and it's going to be dependent upon, all right, is the moon here or is the moon here in relationship to the sun? Just like those currents. I'm sorry, just like those tides. And then you're also going to have your semi-diurnal, diurnal, and mixed currents as well. So if you're in a diurnal tide area, you're going to have your diurnal currents. If you're in a semi-diurnal tide, you're going to have your semi-diurnal currents. Now, how typically does this work? So the charts look, I'm sorry, the graphs look very similar. They are pretty much have time here, and instead of height over here, change it to current speed. And the phase lag, and then just add a phase lag onto the sine wave. So instead of your peak current here, your peak current is going to be somewhere in here, typically speaking. Whereas the water is moving the most, or where the rate of change is most, and your height, you're going to need the largest amount of current coming through. Where the tide, the rate of change is not very high up top, you're not going to need a whole lot of speed to account for that. So you're going to get, typically you're going to get your slacks up at the top, your peak currents somewhere in the middle. Now what affects currents? So currents, we're focusing on this equation right here, Manning's equation. So when we're talking about the actual speed or the velocity of a current, we're talking, it's similar to open channel flow. So that body of water has to move in, and the rate at that speed, or how quickly the flow rate is identified by Q, is dependent upon a whole bunch of things. None of these really matter, but the key one here is this A, the cross-sectional area. So what does that mean? If I have a small cross-sectional area, it's going to change my flow rate. Whereas if I have a large cross-sectional area, it's going to change my flow rate. So the flow rate is going to be dependent upon how small or how wide of an area I'm talking about. And this is kind of intuitive. If you were to take a garden hose, plug it up, the velocity is going to increase a lot, but you're not going to have as much flow rate going through it. So flow rate, whereas if you have a massive channel, you're going to be able to push a lot of water through it, but it might be a little on the slower side than if I was trying to force that same amount of water through a smaller gap. And this is going to come into play in areas where, one that comes to mind is down near Indian River Inlet in Delaware. There is, speaking with the bosun's mates down at that small boat station, a lot of times in the summer, the vast majority of their SAR cases is a boat will break down and you have a large back bay pushing out into the ocean when the tide and currents are at their peak. And it's squeezing through a very small channel, maybe 100 to 200 feet wide, probably just big enough for a few boats to get through. So that current is ripping through there. That he says, the ops boss down there says that it's not uncommon to see close to a 5-knot current ripping through that channel. And a boat will either come into it and not realize what the current's doing. Next thing they know, they're getting slammed up against a jetty because they can't maneuver the boat in the current, or their boat engine will break down and then the current just starts taking them out to sea and they have to go tow them back. And that's kind of where the open channel flow aspect of it comes in of, okay, if I have a really wide body of water, my current speed might not be the fastest, whereas if I'm squeezing it in to a very narrow area and I still have to get the same amount of flow going, or the same volume of water going through there, I'm going to have to be going quicker. And this is where we're going to get into our eddy currents. And the eddy currents, for those of you on rivers, this also comes into play. This is one of the more important ones on rivers too. So the Western rivers, what is an eddy current, first of all? So an eddy current is, we have the current coming this way, we have some type of rock jetty. As the water flows around it, it actually flows backwards and produces a spiral right here. You can get these in the ocean, or in bays and going out to the ocean. They're also very predominant in rivers. On the Ohio River, when I was in West Virginia, this was a major problem because we knew the current was always flowing in one direction. And depending upon how quickly that current was flowing, there were some boat ramps which we couldn't use, even with a rock jetty sticking out trying to break that current, just because it was so much of an eddy current in here that it was impossible to trailer and untrailer the boat. So now what we're going to get into is some, real quickly, because I'm running a little long-winded, some environmental indicators. And what do I mean by environmental indicators? If I look at something, how can I tell what the current is doing? And the best way to do this is something called a buoy tail. So if I have a buoy or a dayboard or some type of sign and the water is pushing up against it, I'm going to get a tail on the back side of that buoy. So if the current's coming in like this, I'm going to get a whole lot of swirls and disturbance in the water on the downstream side of that. So if I see a tail pointing that way, okay, I know the current is flowing in the direction of the tail, or it'd be kind of like an upward pointing V. So the V is going to point in the direction the current is coming from. So if V is pointing like that, current's going that direction. The quicker the current, the quicker that tail becomes. So I'd encourage you, next time you're bored or you're just out near your body of water, take your tide charts with you and compare them with what your current speed and the tide's doing with what the buoy tails are doing. And you'll be able to very quickly pick up okay, if my tail is this long, I know I got a good knot or two current going through there. If I can barely see it, all right, maybe it's only about a quarter of a knot or even slack tide. So what we're going to do now is we're actually going to pull up the NOAA website, or the NOAA data, NOAA websites that I use to get my buoy data. And here we go. All right, so the first one we're going to look at is going to be tides. And you can Google these. So this, if you just Google NOAA tides and currents, these should pop up. And you can do it the way in which I hate, which is where you actually go into the states. I am a picture guy, so I love going to the maps. And then you just click in. I'm going to come to my local area. And then you can zoom in. And we're just going to pick a buoy or a tide station. Oops. So we're going to do this one right here. So what it will show you is it will show you, okay, at 5:44 a.m., I have a high tide at 5.4 feet. At 12:43 p.m. is when I get my low tide. So it will show you your tidal data. And you can just go in and you can click around a whole bunch of them and you'll get that. Now, if you want more of, or if you're more of a graphical person and you don't want the actual text, we actually click on it. So now we're going to click into New Jersey, and I'm just going to, for the sake of time, we're going to pick one near Shark River Hills. And this one will actually show you your sinusoidal graph in the actual presentation. And then you can come in, you can manipulate the different data, your to, your from, you can get longer periods. So definitely use this website, go into your, find the tidal stations in your local area and click through this. So the currents, let me come back to the PowerPoint. Very similar setup from the currents. You can either go into your graphical one where you'll see something very similar, or you can come into it just like this, and we're going to pick Ambrose Ship Channel up near New York. Very similar graph. Now we're just dealing with speed or knots as opposed to height. And then going back, you can do the same thing where you look at the map instead. Narrow down to your local area. And this one, great example, doesn't have one. Well, that one doesn't have one either. This is going to make a fool of me tonight. All right, well, one more, just so I can, yep, nope, okay. So for the current ones, you might be able to get it to work, but if not, you still have the graphical one, which I showed you first. And so with that, I think I'm right on my 30-minute mark, so let's open it up for questions.
Fantastic. So always fun to get into the details. So we had a couple questions did come up, and while people have an opportunity to type in some more in the Q&A function, please, let's look at some that we have already to talk about. And I closed one window, and here we go. So trip planning. For all of us who've planned a cruise, how important are tides and currents to trip planning? And I think every one of us has a sea story that we can share. But Lieutenant, love to hear from you on this.
Very important. And that's going to depend also a lot on the size ship you have, the size boat you have, where you are. If you're in a 20-foot Boston whaler and you're trying to plan a trip, they might not be as important, at least in terms of high tide versus low tide. However, that current chart is going to be very important. And that's where local area knowledge is also going to come into play. So like the story I told down in Indian River, you're not going to try and get through a channel at the peak of the current, and the next thing you know, you're not going to be able to maneuver appropriately in that, or it's going to catch you off guard. Next thing you know, your bow's pointing towards a jetty and you're still going 15 knots, or you're still plowing through the water. It catches your bow and runs you right into some shoal water or some rock. Whereas if you're in a deeper draft vessel, you might not even be able to get in and out of port. Hoisting with a lot of the cutters down in Cape May, they can't moor up at certain low tides. If the tide's too low, they physically can't even get in and out of their mooring. So we have to routinely, they'll reach out to us and be like, hey, we can't hoist past this time. We have to go in and moor up, or we have to wait for tomorrow to come in. Which if they've been out for months at a time, the last thing they want to do is wait an extra day. And even then, the bigger ships, current still is important. On my second ship in Wilmington, North Carolina, it was way up the Cape Fear River. We would routinely get 2 to 3 knot currents ripping down through there. And we were right on the river, right on in the bulk of the current. And there were times where we would have to get pretty tricky to moor up. So if our mooring was here, we'd come way up here. We'd start a turn, we'd start drifting down, cast the bow line off as it catches, or the stern line off as it comes past, and just kind of suck us right up into it. So you might have to get real fancy, or if you have a current coming this way and you're trying to get into it, you're going to be having to crab into that current, and your crab angle might be such that you can't clear whatever gap this is to actually squeeze your boat into it. So they are very important. And just like checking the weather before you go out, it's better. It takes a few minutes to go click, hit print, get the data and be like, all right, this is where I'm going now. How much detail you need to go into it. All right, what's my nav draft? What's the draft? What's the depth? That's going to be very dependent, but it is still very important.
And can I jump in there and bring another point to that? Close to where Lieutenant DeCastre is Cape May at the southern end of New Jersey. There's a canal that runs across the bottom of the state, and there are overhead bridges there. And depending on how tall your mast is, the state of the tide can have a significant effect as to whether you're going to be able to get under a bridge that isn't being tended. Plus, of course, going down the Delaware Bay has very strong currents that are tidal driven.
Good points. Well, here's a fun one. Could tides be calculated through vector math as well?
Yes, if you are very good with linear algebra, knock yourself out. Me personally, I actually slept through that class and you very easily can. And there's an old-fashioned way of doing it, which I learned way back when I was striking BM, where you actually have a tidal station, and then someone way smarter than I has actually gone through all the vector math and the progressions and the experimental data or empirical data, and actually calculated, okay, how long is it going to take that tide to progress? And you actually had to go through flow charts of, all right, it's this time here. Okay, let me go to this down over. And it was tedious, painful, and it went in one ear, right out the other after I took my test. And then I just started using NOAA and all the other ones. But yes, you can do it. I wouldn't even know where to begin. But it is possible. It just would be very encumbersome. And to be honest, there are so many factors that are included in it. So the Manning formula, which I had up there for open channel flow, even when you're talking about a concrete channel, which doesn't have all the depths and the contour differences, it's still not very accurate. Depending upon what piece of literature you read, it's 50% accurate. So if it says 100 and you're between 50 and 150, you win. I would imagine it would have a lot more variability to it as well, but yeah, you could.
So let's talk about time. Do current patterns change in a certain area over time? And since the answer is kind of expected, why does that happen?
Yes, they can. How quickly that happens and how often that happens, it would be very area dependent. So there is no absolute of yes, kind of like your variation. Yeah, your variation changes X amount per year. You don't really get that with tides or currents. What really affects it is the topography of whatever channel or body of water you're talking about. And those actually change over time. Very often we'll do overflights for small boat stations where we'll bring one of their senior BMs up. They'll take pictures, and every few years shoals pop up randomly or they disappear randomly. And this was actually a really big, interesting thing in the Western Rivers portion. Not so much now because everything is dammed up until you get to maybe the lower Mississippi where it's not non-dammed. But shoal water shifted all the time. And a lot of what the old towboatmen used to do is how do I read the water, or the steamboats, how do I read the water to avoid the shifting shoals? Just like that back in the 1800s, even still today, everything changes. That body of water might get narrower, it might get wider, something might start jetting up, they change. how quickly the tide predictions and current predictions catch that, I'm not sure. I think
You're muted, Josh.
The quote of 2021. Bruce typed in an answer, but for everyone who's not being able to see this, how much of the process described is automated on a bridge for shipboard operation?
not, or automated as in the tidal readings, or automated as in the bridge opening to allow someone to come through?
That's a
And that's,
Oh.
I asked the person asking the question to clarify what they were asking. While they're clarifying that question, I had a couple of others that I wanted to put to you. Why is the tidal range bigger in some areas than others?
It has to do with location on the Earth. Is a big thing. So typically, the further north you go, up towards Alaska area, you get larger tidal fluctuations than if you're down in the equator. You get much smaller fluctuations. And let me. Oh, where's my button? There's my button. So if you will kind of take a look here, so even granted, yes, this is just a little doodle that I did in PowerPoint, but it still kind of demonstrates the effects of it. The water up in this area, you have a much larger bulge here than you do down there. So that bulge is going to eventually somewhat move back up, whereas here it stays a lot more constant. So you just get a lot more volume of water moving up in these higher latitudes than you do down here. Now, my explanation might be very elementary and therefore very wrong, as opposed to why, but up in the higher latitudes, you get a much larger tidal fluctuation than you do down towards the equator.
Oh. Fascinating.
I think you've already answered this question, but where can someone get tidal information for their area? And I think you were showing a website for that.
Yes, that is NOAA's website. The links are, I guess it'd help if I share my screen again. The links are right here, NOAA Tide and Currents, and then you'll be able to pinpoint now as to how to locate what specific tidal station is closest to your area. That's going to be dependent upon you. That's where I like the map function. You click the maps, and I might not know where Ambrose Ship. I mean, I do know where Ambrose Ship Channel is, but I might not know the specifics of. All right, where's Ambrose Ship Channel #1? Whereas when you look at the map, you can be like, okay, I'm going from here to here. Let me click that one and click that one. And then if you're going to be in the same area, just write them down, and you'll eventually type them in enough to where you'll know them. But NOAA is the best one, and that's mainly because they're the official one. Now, there are a whole bunch of other apps and websites that you can do, but if you want to be official, go with the NOAA.
Okay. A couple more questions have come in. Why are the tides semi-diurnal on the East Coast as opposed to the West Coast?
That is an outstanding question, which I actually do not know and did not get an opportunity to look into.
Okay.
That is a very good question, though. If I had to guess and just take a shot in the dark, I would imagine a lot of it has to do with ocean topography and ocean currents, such as continental shelves, Gulf streams, Labrador currents, whatever the West Coast has. Once again, I'm on the East Coast my whole life, so I don't know much about the West Coast currents. But I would imagine it have something to do with that. But the exact answer, I'm not entirely sure.
Okay, so we do have a clarification for the prior question. So it's about the bridge of a boat or ship. How much math and modeling is done by a navigator versus what might be automated without a lot of work to save time in making a decision?
So as in, I think my connection was a little bad. So it's more of a, okay, how finding the height of the bridge and the clearance of the bridge, how much of is that automated or?
No, it's
shipboard operation.
right. It's the tidal range. they're talking about the navigator doing voyage planning and how the navigator ought to be doing that, whether they're doing it in advance or whether they should rely on automated means to accomplish that.
Okay, so on the like a ship bridge, not a car. Okay, no, I'm tracking.
Wheelhouse, yeah.
I absolutely do it in advance. The tide predictions are very constant, very predictable. Just like your celestial navigation tables, they're fairly well known. You can go out months in advance. Now, if you're going to be out for 3 months, don't do the whole 3 months, but several weeks or a week or two before you're getting underway, do it for your underway period. And when you're out to sea, you don't really care as much about your tidal currents or tides. Then when you're coming back in, get back on and redo them a few weeks or a few days in advance, because you'll definitely want to know beforehand as opposed to coming up the day of and being like, all right, let me see what's going on. If that didn't get the gist of your question, please re-ask it and I will try again.
I think that was a great answer. I think of trips that my ship has made from Annapolis, Maryland to Cape May and going through the C&D Canal and then down the Delaware Bay, where you have boats that are traveling under slack tide conditions at 5 to 7 knots. And if you have a current that's 3 to 4 knots coming in, you may want to choose a different time to go down the Delaware Bay.
And a lot of that too, how the tides are it's also going to affect your ship's swing radius, which for most people you don't really care about. But when you're confined to that channel, there are certain parts where you do not want to meet another ship. Other words, you will collide. And there's nothing you're going to be able to do about it just because of the way the currents are pushing, and those currents do affect that to some extent. Now, most of the people who are concerned with that are going to be your pilots who have everything memorized to the T. I mean, a pilot has to literally draw pretty much the entire channel, but that is another factor that comes into play with knowing your tides and currents.
Or anchoring, like if there's a 7-knot current, you don't want to put down a 35-pound anchor. Just
that too.
So I understand there's a project that you would like to share with attendees for something they can do on their own time.
Yeah, so the project, it's not so much a written project like the celestial navigation one that I did or the weather one that I did. This one's going to be more pertinent to your actual local area. So what I am encouraging everyone to do and what I want you to do is actually dig into these tide tables and start learning your local areas. Let me share my screen and kind of go over what I'm talking about here. So we're going to come back to these NOAA tide and current tables. And we are going to use, once again, I'm going to stick with an area I'm somewhat familiar with. But since I've done so much in New Jersey, let me come down to the Gulf Coast. Back to my old stomping grounds in Mobile, Alabama. So what I would encourage you to do is, let's say we are planning a trip from Pensacola, Florida, over to Mobile, or better yet, we'll do the Dauphin Island area up into the Tinsall region of Mobile. So what I'm going to encourage you to do is come down in here, select multiple buoys, and actually come through. All right, so let us take the Dauphin Island one. So we'll come to the Dauphin Island one and we'll note, okay, 5:36 a.m. we have a low tide. All right, so where's my next low tide? What is the tidal progression going to be in my local area? So 5:36. Now let's come all the way up here to the closer to the Mobile. Of course, I picked one that doesn't have one. We'll try this one. All right, so low tide's at 7:34. That's a 2-hour difference from low tide here to low tide up there. So now we're going to try, see if we can't pick the same ones, but we're going to use our currents instead. All right, map. Back down to Alabama. And you might have to get creative with it because not all of them are going to stay the same. Like this one, it's not going to give me my current data. All right, well, let me use the graphical one. So essentially what you're going to be doing is you're going to be going to multiple different buoys, progressively going inland, or from a wider body of water or narrow body of water into a wider body of water, and take a look at what the current speeds are doing, what the tidal progression is doing, the tidal progression is doing, and just go through all of these different ones and actually note, okay, as I get further up into the Delaware Bay, the current's going from, let's see, am I still sharing? No, I am not. There we go. We'll actually come up in here. Which one did I? Third time's the charm. Here we go. All right. We'll do the one that I actually practiced on as an example earlier today. But knowing my luck, since I practiced on it earlier today, it's not going to work, and there might be something here. So let us come way up into Philly. Why isn't this working? Okay, well, earlier today it was showing about 3 knots of current. And then way down here at the mouth of the Delaware Bay, we were only showing about 1.5 knots of current. So there's almost a 1.5 knot difference going from the middle of Delaware Bay all the way up into this narrow channel right here. So that's what the project is going to be. Actually take a look at the data and see, okay, how do the tides act in my area? I get a high tide here. All right, the high tide's at what time? All right, now let me cross-check the current. What time is the current? How fast is the current? How high is the high? All right, let me move up a few miles. All right, what's it doing now? What's it doing now? What's it doing here? What's it doing here and at what time? And really get to know the area that you're working in and how the topography of your local area affects your tides and your currents. And then once you have that knowledge or have that data, actually go sit by the Delaware Bay Bridge or the C&D Canal. Take a look. Okay, the tide should be doing this at that time. Oh, wow, that's a really strong eddy current coming off of there. I would not like to be in a small boat going through that. Or, oh, I mean, I can't even really tell that the tide's moving right now. Is it really moving 1/2 knot? What's going on? What's that buoy tail doing? And start to put the pieces together with, okay, this is what the data is showing, and this is what I'm actually seeing. So even if you are caught with your, I guess I can't use that term, even if you are caught off guard, you are still going to have the base knowledge to at least assess the situation and be like, okay, I don't know what the current's doing exactly. I know I'm halfway between a high and a low, so it should be fast. Or I know my high was 4 hours ago, so I'm on the backside of it. I should expect to see this. Oh, yep, look at that buoy tail. It makes sense. Or it could even be an error trap of, wait, why is that buoy tail pointing the wrong direction? Oh, I did miss that thing. Okay, nope, that's good to know. Now I need to go home earlier, or better yet, hey, now I can stay out an extra 6 hours and do some more fishing. So
another important source for that kind of information is the Coast Pilot, which is widely available. They are published for specific chunks of the coast. And you need to, it just provides a lot of useful information of that sort. And of course, cruising guides will sometimes provide similar sorts of information.
And a lot of Sea Scout ships can do this where they meet, if they are able to do so with their unit restart plan and following all the COVID protocols to keep everyone safe. But a lot of places, you can see that. I grew up in Sea Scouts in Redwood City. We can see the effect of that very clearly. And that's true for Sea Scouts all over the country. So if you can go out and do this, it's a great experiment. Oh, another question came in. Are there any good apps for this information?
that I'm not sure. And even so, being a faculty of the government, I couldn't actually endorse a specific app, which is another reason why I'm leading you towards the NOAA website. I'm sure there are. I just don't know of any, and I can't say of any.
I can chime in since I am not an employee of the United States government. Yes, there are a whole bunch of them. There are Tides and Currents apps, and check out the ratings. It's been a while since I've looked at what's come out lately, but there are a lot of good ones that are available. And Bruce is showing his phone, and yes, it's
even though I have tides and current information on my chart plotter on my boat, I have a couple of apps that I have on my cell phone, but I try to plan those out in advance, particularly if I'm going to go into areas where tide and current can be really tricky. On the Chesapeake Bay, going through the Kent Narrows is one of those spots where you don't want to gauge that wrong, because you could wind up slamming into the bridge or another boat or running aground, all of which will ruin your day.
yeah.
I will also make a plug for paper, and I know I'm relatively young, but paper never runs out of battery, and it never runs out of.
Yep.
Agreed. So yeah, there's lots of options. So with that, everyone, thank you for tuning in. We have a lot of great content coming up in the months ahead. And stay tuned. Like, we're going to have a rowing webinar done by a Sea Scout ship in May that's have seen their material. That includes drone footage. So it's going to be a cool mix of live and recorded. We have other programs that we are planning right now and recruiting speakers. So it's the second half of the year is going to be super cool. We got some great stuff lined up. So everyone, thank you for tuning in. Lieutenant, always good to see you, and for your help as well. And everyone, stay safe and stay healthy. Take care.